Hey everybody, I wanted to take a moment to go over and give an introduction on what we call state tables. And we're going to be utilizing these with the D latch and the SR latch when we start looking at utilizing combinational logic to perform a function and then actually using the D latch or the JK flip-flop to store the output of that function in memory. So with the state tables, they're a little bit different than how we look at essentially a truth table, because we consider the prior state, and based off of our general inputs, in the case with the D latch, D and C, or with the JK flip-flop, J and K, we actually change the prior state or hold the prior state of Q. Now, on the D latch, I only consider basically Q prior and then Q next, because Q and Q bar are always opposite of each other, no matter what, and we proved that out. However, with the JK flip-flop, I not only can consider Q current, but also I like to show how Q next and Q bar next actually may reverse each other in that toggle state. So again, this is a little bit different from basically a truth table, because we're actually considering how the state of this logic will actually change. So to give just an introduction, we're just going to go through possible variations of Q prior, and then actually see what Q next will actually do based off of basically that prior state, along with how maybe we may have, in the case with the D latch, D changing, or even how C is enabled or not enabling that D latch. So let's take a look here. So let's say Q prior was 0 and C was 0, so that means that it's not enabled. D is 0, so we would think that would be a reset state. But regardless of whether Q prior was 0 or 1, we're going to hold that to 0, because as long as C is 0, basically the D latch is not enabled. Let's take a look down here. So C is enabled, D is 0, Q prior was 0, therefore Q next is still 0. But here's where the state table actually really helps us see how the functionality is actually working. So in this case, Q prior was 0, D is set to 1, so we want to actually show a set state, but we're not going to be in a set state because C is actually going to be held to 0. So therefore Q next is actually still 0. But now we're actually going to see where C is going to be enabled high, so that means the D latch is on. So D is 1, so we're in a set state. With Q prior was 0, so now we have Q next is actually gone high. So now we definitely hit that set state. If Q prior was 1 though, and D goes low, that means we have the intention of having a reset state where Q is going to go low, but C is 0, therefore Q next is held in memory basically to be 1. Now, if C is 1 and then D goes low when Q prior is actually high, that's a reset state. Sure enough, bam, look what we got here. Yep, Q next actually goes low. So we are in that reset state. Here, C is 0, D is 1, Q prior is actually 1. So therefore we actually hold that. Conversely, same down here. C is 1, so the latch is enabled, but Q prior was 1. D goes high, therefore we are still in a set state, but nothing changes because Q prior was 1. So reading the D latch is actually very, very simplistic to basically do in terms of generating or even developing well, that's the same. Basically that state table. And essentially what we're actually going to see is we're going to see combinational logic that's going to feed in basically for the input of D. And so that's actually the state table is really going to help us understand exactly how this logic is not only functioning, but also how we're actually going to be utilizing that D latch in order to either hold that value or basically reset it or set a value. Now let's take a look at the JK flip-flop and its state table. So Q current, and then we have J and K. So we said with J and K, 0 and 0 was basically that hold state. So sure enough, Q current was 0, so therefore Q next and Q bar are 0 and 1. So that value is held. J and K, 0 and 1, we know that that is a reset state. However, Q current is 0, therefore we have still 0 and 1. However, when J is high and K is low, we're in a set state. So that causes basically the 0 to actually go to high, in which Q next is actually now low. J and K, if they are both 1, that's what we call that toggle state. So Q was 0, so we actually flip those. So we actually get Q next as being 1 and Q bar next as being 0. And as we go down here, J and K, both 0, that means we're in a hold state. Therefore, if Q current is 1, Q next is still actually going to be 1 and 0. Nothing changes. 0 and 1 are reset states. Sure enough, that 1 turns to a 0, in which Q bar is 1. Now, we're in the set state of 1 and 0. Q current is high, therefore those values are just naturally held, 1 and 0. However, here, when J and K are both high, we're back in that toggle state. So sure enough, that 1 flips, we get 0 and 1. So the whole entire point of basically the state table is basically to drive basically a visual kind of understanding of how everything's working within the D latch implementation or the JK flip-flop implementation. So we're going to be now adding in combinational logic, and we're going to be utilizing the state tables to actually show how basically not only the combinational logic but also those values are actually held. So we're going to get right back to that one next time. All right, see ya.